Hello everyone. Today we're going to be going through LeetCode problem 79. It's called word search. This problem is a sort of a spin-off on a previous problem we did. It primarily involves a searching algorithm, and the one before that we did was the number of islands problem. It's somewhat similar to that in terms of the approach that we're going to take. We use depth first search for the number of islands problem on LeetCode. We're going to be using the same principles that we applied when we were using DFS, but it's going to be more of a backtracking solution here. So the way I want to approach this problem is going to be the same way that we approach all problems, is using the STAR approach. For those that don't know, the STAR approach is the best, or it's the industry standard in terms of how you want to approach both behavioral and technical questions. And it's also a pretty good habit in terms of the logical process you follow in terms of approaching these technical problems. So to start, we want to set up the situation, aka what is the question actually asking us. In this problem, we are given a m times n grid of characters, which is called board. And we are given a string titled word, and what we want to do is we want to return true if this word exists within this board. So we want to search for this word within this matrix here. The word can only be constructed from letters of sequentially adjacent cells, so this means they have to be horizontally or vertically neighboring. It can't be a word that's connected or composed of a diagonal connection. And the same letter cell may not be used more than once. That just means that you go, like, for instance, if we're looking for C here, you can't just do S, E, and then E again, for example. It has to be a unique character in order to come up with the actual word C. So if we go through this example right here, the word that we have is A, B, C, C, E, D, or the phrase or the sequence of characters or letters. So the pattern is composed of this path right here, A, B, C, C, E, D, and it matches it, and it's the only unique one here, considering that the other A here does not have any connection to B whatsoever. We need that to actually create the word that was given. And here the output is true, since we actually found a path that is this sequence of characters or the word that they gave us. And the same thing applies here. C is here, S, E, E. This goes from here down and to the left, so no diagonal approach here. And the same thing applies to A, B, C, B, but in this case, if we go to A, we have A, B, C, and then once you get to C, there's no connection to B here, and then same thing here, A, then there's no connection to B. So in this case, we return false because there isn't an actual word that we have. Some of the constraints that we have: m is the board length, so this is just the row size, n is the board length for the specific row for the columns. So just saying here, this is the size of the actual column itself. These are the constraints for the row and column sizes. This is the constraint for the length of the word, so 15 would be the maximum size of the word that we're given. And here the board and word only consist of lowercase and uppercase English letters. As we always do, some of the most requested companies that ask this type of question are Amazon, Microsoft, Twitter, Facebook, and so on and so forth. And yeah, that's the situation. Now, the task that we have is that we want to traverse this board or this matrix in a way in which we find the path of characters that lead us to actually match with this word. So that's our task, and from there we simply just want to return a boolean true or false. True meaning we found the word, false meaning we did not find it at all. So in order to accomplish this, the best way, I would say, whenever you're approaching these kind of problems where you want to search for a path or you want to search for some sort of character set that's unique, for example, I would say the best way is to use a searching algorithm. A couple of them that you guys may be familiar with is depth first search, breadth first search. There's also binary search as well. and so on and so forth. Those are just the most popular ones that come to my head when thinking about it. But the general idea that we want to utilize here is a recursive approach to backtracing. It's going to be sort of a spin-off of DFS. It's going to be very similar to it. But the basic idea is we want to start the process of searching when we hit the first character of the word, right? That would make the most sense, because we wouldn't want to start at the end of it and then work our way back. Unless we flipped it, it would just be too convoluted and too confusing. We don't want to start at B, because then we would have to find A and then go forward after that. So the best place to start is at the beginning of the word here. So here, once we find the letter A, which is the first character in word, from there we want to start our searching. Okay, we want to go to the bottom. S, is that the next character? No. Okay, we want to go up, we can't go up. We want to go left, we can't go left. Then we go to the right, for example. We find B. Okay, that's our next character. We increment the index to C, and then after that we go to the right. Okay, we go to the right, we find C, we add that. We go bottom, there's nothing left. We already traversed this, so we would set this as something that we already visited. We get to C, then we do the same exact thing. We look right, left, bottom, up. Then we do the same thing. E, found D. And in this case, we found the entire word, and then we would return true. If we stopped at A, B, C, C, then we couldn't find E or D, then we would stop there. We would keep searching the entirety of the matrix to see if there was any other path. And if there isn't, we would just simply return false. So that's how we are actually going to accomplish this, which is the action part of the star approach. In the LeetCode solution section, I could show you guys this pretty nice representation of the problem as we go. So here we have the first character of the word, and then we're looking for A, B, B, A, ABBA here. So once we find A, the first character of the word, then we search up. So we're going to search up, left, bottom, down. This just happens, it went right rather than going bottom, just because that's, if you call the recursive call to the right first, then you're just going to get that as the first, path that you're going to go down. After that, it looks to the right, up, down, so on and so forth, and it finds a B in the south direction. And then from there, we have A, B, B, and then the recursive call is going to be called on B to search around it to see if we can get this last matching character, in which case we do, which is A here. Then after that, we just return true. Okay? Pretty simple once you think about it. Some of these problems, I especially had a problem with the matrices, and it's kind of a little bit hard to wrap your head around at first. But once you kind of get the hang of DFS and other searching algorithms, it's not too complicated. Okay, so here, right off the bat, we want to create a variable to store our final result. This is optional, but I just think it's best to do this. It makes your code look a little bit cleaner if somebody's reading it. So here, our Boolean value is does word exist? And we're going to set that equal to false initially. Here I always like to start off with a couple of edge cases just to make sure that that the input that we're getting is not abnormal. So here I'm going to check if board.length is equal to 0. Oops. Board.length is equal to 0, or board.0.length is just checking that we don't have any columns. Sorry, this should be an and. This just means if we don't have any rows and we don't have any columns. Equals 0. And then here we just want to check if or board equal to null, or word dot is empty. And here in this case we simply just want to return the word does not exist. So does word exist? It's going to be initially equal to false, so we just want to return that in the case that any of these actually happen. Sometimes with the test cases with LeetCode, there might be just a couple of random ones in my experience, so I just want to check for those right off the bat. In the case that we don't have any abnormal input, then it's pretty standard with any matrix problem to have two for loops. So this first one is going to be traversing the rows for int I equals 0, I less than board dot length I plus plus. Then this is going to be for int j equals 0, j less than board. Then here you do I dot length j plus plus. The reason why to get the columns we put I here, it's saying at this given row how many values or how many rows underneath it do we have, which essentially is the columns in this case. Yeah. Okay, so now that we have these two for loops, like I mentioned earlier, we want to start the actual searching algorithm at the point where we find the first letter of the word, right? So in this case, we want to check if board I j, this is how we're traversing the 2D matrix, so I is the rows and j is the columns again. If this is equal to word dot char at I, then here, so I apologize, not I, it should be 0. So if the board at the current position, so say for example, in this one, we're going to keep traversing 0, 0, 0, 1, 0, 2, 0, 3, and then here's 1, 0, 1, 1, 1, 2, 1, 3. At this position, the value of the board at ij is going to be equal to the first character in this word, right? So in this case, we're going to start our searching algorithm from here, right? So in this case, we are going to do two things. So we want to check for two things. So we want to check if this is true. So if the board at this position is equal to the word, the first character of the word. And then here, we want to have another if statement that checks if, we're going to be writing this method in a minute, if backtracking, this is going to be our search algorithm. Let's see, is equal to true. Then here we want to return, or here we want to do does word exist is equal to true. Oops. And then return does word exist. Okay. And then here, let's move this here, else in the case that the board is not equal to the word .char at 0, so the first character, we simply just want to continue on with the for loops. They're going to be traversing the rest of the matrix. That is all for the for loops here. So that's the entire logic you're going to have in this. And I'm going to split up the rest of the logic into its own separate function. So here we're going to have private boolean, since this is going to return true or false, the backtracking if it found something. Backtracking. We want to pass in a bunch of things into this, okay? First thing we want to pass in is the actual board, so we do char, oops, then we do board. We want to pass in the word. We want to pass in the indexes in which we found the items. And then we want to pass in the, let's see, where was it? Actually, yeah, we want to pass in the index that we found, so int word index. So this is Okay, think of this in the first time we're going through. So we know that we're going to be starting off at the beginning of the word, right? This is going to make a little bit more sense as we explain the rest of the problem more within this method here. The word index originally is going to be 0, so it's going to be starting off at the rest of the word, at the beginning of the word. But as we continue, we want to increment this as we're making the recursive calls of backtracking, and then this word index is going to get incremented to E, and then to the next E, and so on and so forth. This is just a way of us recalling the recursive call multiple times with different parts of the word that we're trying to match. It just makes it a little bit easier on us, and it makes the recursion process a lot more effective. Okay, so here, actually before we do that, let's feed in the values here, board, word, I, J, and then here is going to be 0. That's going to be the first character of the word. So here, our terminating condition for our recursive calls is going to be if the word index is going to be equal to the word dot length. So here, this is going to be our terminating condition for recursive calls. The only reason this is a word dot length and not word dot length minus 1 is because our word index is going to get incremented one last time, so it's going to be the actual length of the word rather than word dot length minus 1. It's just the way our recursive call is going to be, so it's going to increment one more, and then after that it's just simply going to terminate. So here we want to return true. So if we get through the entire word, so we find a match for S, E, and E in this case, we will return true. The word index being the same size as the word length would mean that we found all the characters in this case. Here we want to have another if statement to actually check for boundary conditions. So in the case of A here, the recursive calls are going to be generalized to all of them, so we're not going to have separate recursive calls for the values on the outside of the board, just all going to be the same, but we want to make sure that we're not going or exceeding the boundaries of the matrix. So we're not going up, we're not going left for A, and so on and so forth. So here we want to see if I is greater than J, sorry, if I is greater than, if I is less than 0, or I greater than, let's see, greater than or equal to, let's see, what's it called, board dot length, or J is less than 0, or J greater than or equal to board I dot length. So this is checking the rows to make sure we're not exceeding any of the row values. This is checking the columns, make sure we're not exceeding any of the column values. We also want to check that our what's it called? Let's see. We also want to check that the current position that we're at, board I, J, actually equal to something, is actually equal to the word dot char at word index. We're going to be adding one more thing to this as well. But just like I said, this is checking the rows, this is checking the columns in the J portion of it, and this is just making sure that the current position that we're at on the board, what's it called? Making sure that actually equals the current character that we're at. Hence, that not if it's not equal to it, then here we want to return false. Okay. And then here we want to, okay, so in this case, let's do this. So what we want to do here is we want to actually increase the index plus plus because we want to move on to the next, the next word. Now, right before we go into the logic of this, I just want to explain one more thing that we have to actually add. So every single time we go through an index and it comes out that the current character there matches up with a character in our word, so S and S here, we actually want to have a separate 2D array that will keep track of what values we visited. So in this case, we want to create another matrix. I'm going to make it global. So Boolean, and this is going to be visited, I'll just say visit characters. And then here, we'll just make it does word, visited characters is equal to new Boolean. In this case, we already know the size, so this is going to be board.length for the rows. And board 0.length. Okay, this is just going to be the visited characters. Now here, right before we increment, we want to do visited characters ij is equal to true. So all of the visited characters now in this are going to be set to false, and then now we just want to set them to true, meaning that we just visited them, or we want to set this given position to true, meaning that we visited them. We increment the word index, and then in this case, so we are, or I'll just go back to this example. In this case, if we find a, which is going to be here, board ij equal to word.char at 0. In this case, we want to call the backtracking method that we're writing down here. We're passing in the board, the word the position that we found a, and then we're passing in that this is the first index of the word here. And then once we go into this method here, we're checking is the given word index now equal to the word length, in which case we have a match and we will return true. Here we are checking the edge cases just to make sure we are not exceeding the boundaries. And then here we are setting the character that we visited, so we're setting a to true, as in we did visit this character before, and then now we're increasing the word index. So now we're going to go on to B, and we're going to search for B within the space of the recursive calls that we're going to make on A. Here we want to add one more thing into the edge cases. We want to see, or visited characters ij true. So you're just making sure that the current position that we're on, we didn't already visit it, because if we already visited it, we don't want anything to do with it, because we can't have the same letter cell be used more than once. So in this case, we have to make 4 recursive calls. So I'll write this one, and then the rest should be pretty self-explanatory. Pass in board, pass in word, pass in I, pass in j, pass in the word index. here, for this one, we want to go to the right. So I plus 1 represents going from A to B. So I'll just make a little right. There's here we want I minus 1. So here we're going left. Here we're going to go up. So in this case, the row stays the same, but we want to increment the column itself. And then here we're going to be going down. We're going down now. So these is the if statement. So if any, oops, these shouldn't be, these should be ORs. So if this returns true, if going to the right returns true, that means that we have a match for the next character. If going left returns true, that means we would have a match, and so on and so forth. So essentially we're going to be following the path or the recursive call that is going to be taking us down the correct path. We won't be going down, for instance, S, and then keep on calling the recursive call on that, because we already know A to S is not going to work because that already breaks the sequence of the characters that we have inside this word. So we are only going to follow the actual path itself and keep on making the recursive call towards the path that seems correct or seems ideal in the moment. So in this case, we want to return true if these come back as true. If any of these come back as true, meaning that we would have a path from this one. In the case that we actually don't find anything, that means we're going to have to go back to these two for loops, and we're going to have to continue on with the matrix and continue on traversing it. So let me just denote this as columns. So we're going to have to go back if we don't find anything. So in this case, we would do visited character. I'll explain this line in a second. IJ is equal to false. Okay, so I saw on the discussion forums that this was kind of stumping a lot of people as to why we have to set this to false. So think of it like this, right? In this case, say we're looking for A, B, C, B, and we know we're not going to find it since this is the given output that we have, right? So we go to A, we go to B, we go to C, right? These all come back as what? True, right? We're following the sequence of A, B, and C, and seems to be going okay. We just have to look for this final B here. Then after that, we simply return true, and it would be a full match, right? But in this case, we actually don't find it, right? So what we need to do is, okay, these weren't part of the ideal path that we needed in order to come up with this word, but that doesn't mean that other paths may not use these characters in order to actually come up with this word. So in this case, if we find another A in this sample, say for instance another B was here, or say for instance, okay, let's see. Okay, I'll repeat that. So here in this case we have A, B, C, and then we're looking for B, we don't find it. We want to set these back to false, meaning that we can reuse these for future paths if we will need the C or the C in order to actually come up with the finality of this word. But yeah, and in this case we would just simply return false, meaning that we didn't find anything for this given start of the path. But yeah, this should be right if everything works. Let's see, let's run the code. Of course, some errors. Line 50. We don't need this. Let's run the code. Can't find symbol. Oh, I called it DFS here. This should be all backtracking. Missing return. Yep, that's going to be important. Return does word exist? There we go. So our output came back as true for this. Now let's submit, see, hopefully we pass all test cases. Alright, there you guys go. This was faster last time I ran it. Let's try it again. Not that it really matters, as long as you get a solution. Oh, there we go, that's a better number. So the action part of the star problem was actually completing it, and now it's time to discuss the results. So we were able to pass all the test cases that they provided us on LeetCode or whatever the assessment may be. And in this case, if we want to go a little bit more in the time and space complexity, the solution itself outlines this pretty well. So in the particular way that we tried to solve it, it was somewhat similar to the solution that LeetCode provided, but it's kind of a spin-off on it. This one didn't really make sense to me when I was reading it initially. Just the notation seems a little bit off. So, but the complexity should be the same exact thing. The time complexity should be big O of n times 3L, where n is the number of cells and L is the length of the word to be matched. The reason why it is 3 rather than 4, because you originally say, okay, we have 4 directions to explore, but the reason why it goes down to 3 is that we know that we're not going to go back to where we came from in this case. And then the n is simply the number of cells on the board, so we know we're going to have to invoke that n times, at worst m times, in which case that we get the number of times that we might invoke this recursive call times the number of directions that we can get in order to get the time complexity. And the space complexity is simply just going to be the recursive call stack that we talked about, and at most it's simply just going to be the length of the word, because as we mentioned before, we're going to be going through each one of the characters of the word itself, and that's as and that's the worst case that we could possibly have for the space complexity in this case. Thank you guys for watching, and let me know if you guys have any questions in the comments.